Hello everybody and welcome back. We are going to keep going on our OpenAI Gym project, which is the final project for our introductory course. So hopefully you got your OpenAI Gym environment all set up last time, and I've kind of cleaned up the code that I was using. I added in some comments here, and everything's installed and importing correctly. If that's all set up, then we should be good to go. A cool thing about Jupyter Notebooks that I'd like to share really quick is that you can include markdown cells. So if I have a cell like this, I can simply go up here to cell type and change this to markdown. Now I can type comments in this that won't be ran as code. So for example, I can do 2 here, and I can say define parameters, because that's what we're going to be doing. When I do Shift Enter and run that, it just produces text. So if you're going to be sharing Jupyter Notebooks, this is such a valuable resource. Include markdown cells because they're very helpful to explain what's going on. So hopefully you guys have access to this project and you can see some of these cells and read them as such, because they're very helpful. But that being said, let's keep going. We're going to start by defining the parameters that we're going to use for our network. Then we are going to get into actually building the neural network and defining some necessary functions, such as a run function, some pre-processing functions, and then we can actually get into training the network. So let's take a look and see how this works. Alright, but first we have our training parameters. So we're going to have to specify these. We'll start with the number of episodes, and we're going to run this for 1,000 episodes at most. And the number of winning ticks. So in the OpenAI Gym environment, every time step is called a tick, and so our done state or our winning state is either going to be when our poll tips over, and that is it gets, I believe the parameters are larger than 15 degrees from the center or outside the bounds of the little window, or we hit the number of winning ticks, which is going to be 195 time steps. So max environment steps we need in there as well. This is for the OpenAI. We'll set this to none. Alright, now let's get into some actual reinforcement learning parameters. We're going to start with gamma. And gamma is, of course, the discount factor. And we're going to set this to 1. The discount factor does a couple things. Really, it's what it is simply is a consideration of future rewards. So this is going to say, should we take this step even though it might not be the best right now, but it could give us a good result in the future? We're going to set this to 1 in each case because we want the same policies, the ones that are going to balance the poll, to be optimal at all times. So that's why we're setting this to 1, and that's the discount factor. We're also going to have epsilon, and we're going to set this starting at 1 as well. And this is a factor that controls what's called exploration. So exploration is simply the agent choosing an action that it believes has the best long-term effect with a probability 1 minus epsilon. So and it's going to choose an action uniformly at random otherwise. So starting with epsilon at 1, it's going to choose a uniformly random choice. So it's not going to use any type of machine learning. It's going to randomly pick a direction to go, or a random force to use. I mean, this is a great way to avoid local minimum, but we don't want to be making random steps the whole time. So what we're going to do is we're going to have an epsilon decay and an epsilon min. So we're going to start with high exploration, just taking random steps, and then we're going to immediately start lowering this. So by the time we figure out how to actually balance the poll, we don't want to do any exploration anymore. We figure that's the correct solution, we can stay. So let's have an epsilon min, and we're going to set this to 0.01 and an epsilon decay, so how quickly it is going to stop exploring. And we'll just do 0.995. So there is our decay. We're also going to need alpha, and alpha is the learning rate. Remember, this is going to determine to what extent the newly acquired information will override the old information. So if we had a learning rate of 0, we wouldn't learn anything at all. If we had a learning rate of 1, we would only consider the most recent result. But let's also have an alpha decay. So we're going to lower this as well. Also, we need a batch size. So let's include that in here. Just for starters, let's do a batch size of 64 samples. And then this is some stuff for the OpenAI gym specifically. We're going to just do monitor equals false as well as quiet. And quiet we're going to use to control our print statements. Alright, so those are our training parameters. We also need to get into some environment parameters to specify some stuff for the AI gym. So let's type this. Parameters. Alright, and so what we need is a memory. And I guess this kind of is and kind of isn't part of the environment. And we're going to use that custom list parameter that we imported before, so we can set a max length to this list. And we're just going to do 100,000. Yep, that's 100,000. So we can control the max length. This is really just a list with some additional requirements with it. Our environment, we're going to do the gym.make, remember, and this is the cart pull. So there's that. And we're also going to have this if statement in here. And if that is true, we can do the environment max episode steps equals max environment steps. Alright, we're going to also need that as well. So these should be good to go. Let's just shift enter, run that. Oh, I need to run my import statements again. So what I'm going to do is going to do a restart, clear all output, and just run all. And that way it'll go through all my import statements at the start again and import the correct libraries. It's going to clear the output and you'll see them coming back up. So look, there we go, 2.7, importing all this. And this guy's still going. Let's see. Let's stop that. I'm just going to click stop here. That guy's messing us up. But these we can just go through. These are all the same, define parameters. Awesome, there we go. So all our libraries imported. We've got our environment. So let's move on. And we want to actually move on to building the neural network. So this is going to be a fun part. We're going to actually get to specify some parts of the network, but first we need to import some other modules. We already imported that, but we need from keras.models, we need the sequential model, since that's what we'll be building. And we need a couple layers. Import dense. We want the dense layer, which is again just a fully connected, the standard neural network layer. We're also going to use the Atom optimizer. Alright, so now let's put up our model definition. So start, we define what type of model it is. Well, it's a sequential model. So there's that. And then we can start adding layers. So we want a model.add. And we're going to start with the dense layer. And this is going to have 24 neurons on it, but it's going to have an input dimension of simply 4, because remember our environment has 4 parameters that describe the current state of the environment. So that's why we want an input of 4, because our input is the current environment. Activation, again, is just going to be the rectified linear unit. And there's that. So there's our first layer. Let's add a couple more in here, because we want to build a deep reinforcement neural network or reinforcement algorithm. So we're going to have a couple hidden layers, and so we're going to add those now. And so we'll do that. Dense, we'll have this one expand a little bit. Don't have to specify the inputs anymore, since it assumes the previous layer is the input, since it's sequential. And let's add one more, and we're going to do dense, and we want this to go down to 2, because remember, our action is either a force to the left or a force to the right, so we want 2 possible outputs here, and that's why we're coming back down to this output of 2. Alright, so there's that. We also need to say how to compile this. So model.compile loss, which is the MSE, and then the optimizer again is equal to the atom. And so learning rate, we already defined that. That's just alpha, and then the decay is alpha decay. And there we go. So there's our network, and this should all compile. Let's try that with a shift enter. And it's building, and yes, everything looks good. So no typos this time. That's good. We have our model definition, and we've compiled our model. It's a neural network with 3 dense layers, all with the rectified linear units as the activation. Input dimensions of 4, and then an output of 2, which is going to be our force. A force to the left or a force to the right. But before we actually get into training this, we're going to have to define some necessary functions, because these are going to come up a lot of the time, and so we need to get these out of the way now so that we don't have to type them in a bunch of different times. We're going to have a function remember, a function choose action, get epsilon, preprocess state, as well as replay. So the first one, remember, is simply going to be setting up our memory, which, remember, was the list that we imported earlier, right up here. So this is going to have the state, the action, the reward that we got, the next state, and the done, whether it was done or not. So here's our definition, and we are just going to do a memory.append. And so we have a state, action, reward, next state, and done. So we're just going to append that to our current memory. So that's that definition. We're going to have another one here, and this is the choose action. So this is where we actually pick what to do based off the state and our epsilon, which, remember, is our exploration factor. So this is going to change depending on the value of epsilon. So what we want to return here is the action space sample. And if we have the NP, which is numpy, random number, and this is actually less than or equal to our epsilon, it's going to choose this random action. So at the start, when epsilon is equal to 1, this is going to choose a random action here and randomly from the action space. If not, what we're actually going to get is our model making a prediction based off the current state. So what does our model think that we should do given that our environment is in this current state? So starting random, if we're in an exploration stage, at the end we want our model to be predicting the force and direction that we should use. Alright, so there's that definition. We also need a def get epsilon. So based off t, where we are in the episode, we're going to return the max of epsilon min, or the minimum of epsilon, or this here, log 10 t plus 1 times epsilon decay. So towards the end, we're going to be decreasing substantially. At the start, we're going to be right up here at epsilon. So there's that, and that'll come up fairly often. We're going to have a preprocess the state, and this is simply to make sure that it is in the right input format. So we are going to return the numpy reshape of the state and simply transpose it into a column here. So 1 row, 4 columns, and that should be good to go. Alright, finally, last one is we have the replay. So this is going to be important. So let's go through this, and it's going to be based off the batch size and epsilon. So we're going to have to define a few things here. We're going to have an X batch and a Y batch, and those are going to start out as such, just empty lists, we're going to have a mini batch. Random sample. So randomly sample from the memory, or the minimum of length, memory, and batch size. Alright. And then what we're going to do, so we're going to have a for statement here for the state and the action and reward, next state, and done, which we're getting out of the memory in our mini batch, which we randomly just selected. What we're going to have is a Y target, and this is what our model is going to predict. So model.predict state, so that's the target, and then Y target 0 and action equals reward. So we're going to get a reward if that's the correct target to be predicting. So if done, else, a reward, and this is gonna where gamma comes in, times the np max model.predict next state.